Good morning. Myself, Dr. Amish Srivastava. I am professor in CSE department, SIIT Bhopal. So today we will be studying the topic neural network. Now let us see, first of all, what is linearly separable problems. Now suppose we have got the red balls and the black balls, and I want to separate out these red ball and black ball with a single line. So we can do it like this. So if we can do it, if we can separate out these red ball and black ball with a single line, then I will say that it is a linearly separable problem. Let us look at another example. Now, this is our AND gate. The input of AND gate is 0, 0, 0, 1, 1, 0, and 1, 1. And the output will be 0, 0, 0, and 1 respectively. If I plot this inputs and outputs in the XY axis, then it will look like this. So 0, 0 with output 0 will be marked here. 0, 1, that is x-axis is 0 and y is 1. And the output 0 will be marked here. Similarly, 1, 1 will be marked here and 1, 0 and with output 0 will be marked here. Now, if I want to separate out these outputs 0 with the output 1, then we can do it like this. This dash line is separating out these output 0 with the output 1. So I can say that this AND gate is also linearly separable problem. Similarly, if I plot this OR gate in the XY axis, and I want to separate out these outputs 0 with the output 1s, then I can do it like this. This dash line is separating out these output 0 with output 1. So again, I can say that this OR gate is also linearly separable problem. Now, let us see the case of XOR gate. Here, the output will be 1 when the inputs are 0, 1 or 1, 0. And the output will be 0 when the inputs are 0, 0 or 1, 1. Now, if I plot this XOR gate in the XY axis, then we can see here that I cannot separate out these outputs 1 with this output 0 with a single line, right? So this XOR gate is not a linearly separable problem. So what is the difference between linearly separable and non-linear problems? So the linearly separable problems can be solved by a two-layer neural network. But the problems which are not linearly separable, we will require minimum of 3 layers neural network. That is the input layer, output layer, and the hidden layer. And why is that so? So let us look at this diagram. Now, these are the input layer neurons, and this is the output layer neurons, and the interconnection weights are like W11, W12, etc. So in case of linearly separable problems, these outputs are not dependent on each other. Okay. Now, first of all, let us understand in this neural network problem, what are the changeable things? Now, suppose since this neural network is a supervised learning mechanism, it means that we have already got the data set. We have got the set of inputs and the set of outputs. So these set of inputs we will be taking from the data set. That is, it cannot be changed. The data which is present in the data set had to be taken. The outputs y1, y2, etc., we will be calculating using some formula, and that formula will be fixed. So these predicted outputs will also be same, cannot be changed, and the actual output will also be coming from the data set. That is, they can also not be changed. So the only changeable thing here is the weights. Now, in case of two-layer neural network, what happens? These outputs are not dependent on each other. So when these are not dependent on each other, then we can solve these using the two-layer neural network. But in case of the non-linear problems or the problems which are not linearly separable, these outputs, let us say this is my input layer, this is my hidden layer, and this is my output layer. So in this case, these output neurons or the outputs are dependent on each other. That is, they are interdependent. Now, as we have already seen in the previous slide, that the fixed things are the inputs, the predicted outputs, the actual outputs, and the only changeable thing is the weights. So in this case, if these outputs are interdependent, or they are dependent on each other, then I require the changeable thing, one changeable thing, from where if I change that, then all the outputs get affected. So in the previous case, there is no such weight, as we have already seen that the weights are the only changeable thing. So in here, no weight is available. If I change W11, then only the output Y1 will be changed. If I change W12, then only the output Y2 will be changed, and so on. So there is no single weight through which if I tune that weight, then all the outputs get affected. But when the outputs are interdependent on each other, then I require at least a single weight, which if I change, then all the outputs get affected. So here in the 3-layer, if I change this WK, then the output of this hidden layer neuron will get changed. And this output hidden layer neuron is connected to all the output layer neurons. So in this case, all the output layer neurons gets affected. So we have got this WK, which if we tune, then all the output get affected. So that is why we have to go for the 3-layer neural network when there is a problem which is not linearly separable. Okay. Okay. Now in the neural network, these weights get updated using a principle known as gradient descent principle. So whenever we want to minimize any function, cost function or loss function, etc., we use the gradient descent. If we want to maximize any function, then we can use the gradient ascent principle. Now let us take an example. This is a line equation. So y prediction is equal to mx plus c. This is the equation of the line where m is the slope, x is the independent variable, c is the intercept, and y is my prediction. Now, if I want to find out the error, then what I can do is this y prediction minus y actual, the whole square. We are doing the square because we don't want the negative values. We just want the magnitude of the error. And if we also find out the mean of this, then I can say that this is nothing but mean squared error. Okay. So now error becomes like this. Mean of this y prediction can be replaced by this mx plus c. So mx plus c minus y actual, the whole square. Now here, this y actual is coming from the data set. X is also coming from the data set. So these are not changeable. The only changeable thing is m and c. And if this m and c can be changed in such a manner that after every change, this error is reduced, then we can increase our accuracy. So this is what is done in the gradient descent principle. So what happens? Let us say we want to change this m. So how I'm going to change this m? So the new m will become equal to old m minus del E upon del M. Now del E upon del M is partial derivative of error with respect to partial derivative of M. It means what is the total impact of this M on the total error? This is what I'm trying to find out in the partial derivative of error with respect to partial derivative of M. So what I'm doing, I'm first of all finding this impact of M, which is affecting this error, and then I'm subtracting that portion from the original m to get my new m. Similarly, I can do with the c also. So c is equal to c minus del E upon del c. So partial derivative tells us the direction in which to move to reach the minima, that is towards the minimum error. Now let us look at this example with the help of a diagram. So suppose this on the x-axis I have plotted the m, and let us suppose I am at present on this portion, okay, where my arrow is showing. So here, and this is my local minima, or this is my minimum point of error. So what I have to do, if I see that m is here, then I need to reduce m to reach to this minima, to reach this minima. And when I reach this minima, then my accuracy will be highest and my error will be minimum. So what happens when I do the partial derivative of error with respect to m, and m is at present here, then it will give some positive value. Okay. So let us again look at this formula. So this del E upon del M will give me some positive value, and this positive value will be subtracted from the original M. So it means the new M will be a little bit smaller than the older M. Okay. Now this is what we want also, because ultimately we want to reduce this M, because as we go on reducing this M, we will finally reach this global minima, and this is where we have to reach. Similar will be the case here. If my M is here, then when I do the partial derivative of error with respect to partial derivative of M, then it will give me the negative value. So this negative value, when I put it here in the formula, then this negative and negative becomes positive. It means I am adding some magnitude or some value to the older M. So my new M will be a little bit larger than the older M. And this is what we actually want, because here we need the M is lying here, and we need to increase the M so as to reach this minimum. And this is how this principle works. Now what happens, sometimes this partial derivative has high value. Then what happens, that it will never move slowly towards the minima, but it will move to and fro like this. Suppose I am at present here, and I need to decrease the M. So if the value of the partial derivative is very high, then what happens, I will get to reduce the M, and it will not jump. It will not come here slowly, but it will directly jump to the negative side. And when I'm on the negative side, and if the value of the partial derivative is very high, then it will jump to the right side. And so it will just jump to and fro from left to right and right to left, and it will never converge. So to move this M in a very slow and steady manner, we make use of alpha, that is learning rate, to move my M in a gradual manner. Okay. So now our formula or our equation becomes like this: M equal to M minus alpha into del E upon del M. So this alpha will be controlling this partial derivative value. If this value is very high, then we will never be able to converge to the global minima. So what we are doing, we are multiplying it by some factor alpha, and typically this alpha can be 0.001. So it will lower down this value to a very small value, so that when we update this M, then it will move very slowly. So that is the purpose of using this alpha or the learning rate. Okay. Now back propagation is the technique which is a supervised learning, which we use in a supervised learning algorithm for training the neural networks. So first of all, let us look what do we mean by this back propagation. So how it works. So this is our model. We are predicting weights based on the initial weights. Now we will calculate the error. Is the error reached to the minimum level as per our requirement? Yes, then my model is ready for doing the future prediction. And if no, then we need to update the weights, because the only changeable thing in this neural network will be the interconnection weight, as we have already seen. So we will update the weight, and how we are going to update the weights? By using the gradient descent principle, which I have just now discussed. So we will update the weights, again do the training, again calculate the error. Have we reached the minimum error which we desire? If no, then again we will update the weights, and so on. So this process will continue till our error is reached to its minimum level. Okay. Now let us solve this using numerical. So you are going to understand what exactly how exactly this backpropagation technique works. So suppose this is my input layer, neurons I1 and I2. This is my hidden layer neurons, that is H1 and H2. And this is my output layer neurons, O1 and O2. These are the interconnection weights. 0.15, that is W1, which is the interconnection weight between the I1 and H1. Similarly, 0.20, that is W2, is the weight between this I2 and H1. Then this 0.25 is the interconnection weight between the I1 and H2. And the 0.30, that is W4, is the interconnection weight between the I2 and H2. The bias is 0.35, which is going to both H1 and H2. Bias, we add the bias to our neural network for decreasing the error or for increasing the accuracy. These are my inputs, that is 0.05 and 0.10. And these are the interconnection weights 0.4, 0.45, 0.5, and 0.55 between the hidden layer and the output layer neurons. 0.01 is my actual output, which is coming from O1. That is, this I have done, I have taken from the data set. Similarly, 0.99 is my actual output, which I require from the O2. Again, this has been taken from the data set. So now what our learning process will be, we will use these weights and the inputs, and we will calculate the predicted outputs. Then we will compare this predicted outputs with the actual outputs and see what is the error. Then after seeing this error, if we are not satisfied, that if the error is more, then what we are going to do, we will apply this backpropagation technique. That is, we will update the weights, these weights, using our gradient descent principle, and again do the same process. And again, we will be calculating the error by subtracting the predicted output with the actual outputs. And again, we will see that whether the error has reached to its minimum level. If not, then again, we will follow the same process. Okay. So now, first of all, let us see how it works. So first of all, we have to calculate the total input, which is coming towards the H1. So here, the total input which is coming to H1 is this weight W1 and this weight W2. Okay. So what the total input which we are receiving at H1 will be I1 into W1 plus I2 into W2 plus this bias B1. Okay. So this is how my formula will be calculated. So in H1 is W1 I1 plus W2 I2 plus B1 into 1. So from there we will be putting the values, and now this is my total input which I have received at H1. Now suppose we are using the activation function of sigmoid. So the output from H1 will be activation function applied over this total input which we have received at H1. So 1 upon 1 plus e to the power minus x. So out H1 will be 1 upon 1 plus e to the power minus 0.3775. So if we calculate this, then we are getting this 0.59326. So this is the output of H1. Similarly, we can calculate the output of H2. Now, once we have calculated the output of H1 and output of H2, then we can calculate the total input which we are getting at O1. And similarly, we can calculate the total input at O2. How it can be calculated? The output of H1 multiplied by this W5 plus output of H2 multiplied by this W6, that is 0.45, plus this bias B2, which will give me the total input at O1. Okay. So this is how I'm going to calculate the total input at O1. In O1 is W5 into out H1 plus W6 into out H2 plus B2 into 1. So putting out the values, this is the total input which I have received. Again, the output from O1 will be the sigmoid function applied over this total input which I have got at O1. So 1 upon 1 plus e to the power minus 1.10590. So this is the total output from which we are getting from the O1. Similarly, we can calculate the output from O2. Now, this is my predicted O1, that is 0.75136, and actual O1 is already given in the diagram, that is 0.01. So actual output is 0.01. Predicted output from O2 is this, which we have calculated, and the actual output is 0.99, which is already given in this diagram. Okay. So now we want to calculate the error. So E total will be summation half into actual minus output the whole square. So half into EO1 will be half into 0.01 minus 0.75136, the whole square, which is coming to be 0.27481. Similarly, we can calculate the EO2, which is coming to be 0.02356. Now, when we total up E01 and E02, then this is my total error, which I am getting after my pass 1, 0.29837. Now, if I want to reduce this error. What I'm going to do, I'm going to apply the gradient descent method for updating the weights. So once, so we will be updating the weights, and then again we will be following the same process, and again we will be calculating this error. So for the next time when we calculate the error, then it will definitely come definitely come less than this, because we are applying the gradient descent principle, and its property is this, its characteristic is this, that whatever function we pass on it, like suppose here I want to update the weights, so whatever thing I am passing it, it will be making that parameter to reach the global minima. So weights will be updated in such a manner that it will give me lesser error in the next pass. So we have to do this repetition till we get the desired level of accuracy. Okay, so that is all for this lecture, and so thank you. We will see the remaining part in the next lecture.